So far in Transformer series, we saw how attention works and tokens generated autoregressively. But this autoregressive nature of models raise a complex problem during inference, which comes with a serious cost like memory shortage in the world. Let's understand how LLMs are started eating memory. But before that, if you are not aware of how LLMs predict next token, then please watch those videos first. The link for them is in the description. We know LLMs attain all previous token and use them as a context to predict the next token. Let's see using this example. And a very naive transformer with one attention head and a single layer only. By assuming each word as a token, we'll pass the first token and then it will generate the next token by going through attention mechanism. Let's break down the steps and see how operations are working inside attention head. Inside this self-attention layer, the input tokens are first projected to these three famous vectors: query, key, and value. Where query represents what the current token is asking, key represents how relevant each token is, value represents the actual information each token carries, and by using these three we can compute attention. But keep your attention especially on key and value, they matter the most throughout the video. Let's take an example to understand the problem and then we will reconstruct the theory behind KV cache so that you can understand it by intuition rather than memorizing how it works. We'll set up our tiny naive model with embedding dimension 2, a single layer and a single attention head with these projection matrices, which we can say the model learned during training. And we'll take arbitrary input embedding for each word. Now let's begin with step 1 to get the projection for key, query and value. Now we can compute the attention using this equation. This is original attention formula where the only change is to incorporate values of key and value from 1 to current token t, and is identical to causal self-attention. If you are not getting it now, no problem, everything will make sense, just stay with me. Output of this will be our next token, which is time. Now we'll repeat the process again, which includes computing projection for query, key and value for both first and second token, then pass through attention and other layer to get the next token. Again, we'll repeat the cycle to get the fourth token. And if you are with me so far, then what you are thinking right now is what researchers thought as well. Why not start to store these numbers to avoid recomputation every time since they are not changing, right? But how much difference can it make? Let's see how many operations are needed to get the 5 tokens for the given example. First will be the cost of the linear projection. And since we are performing for query, key and value, it will be 3D square. Second is the cost of attention. For computing dot product of query and key for each head, it will be t times dh, which will be t times h across all the heads. Then for computing this part, the cost will also be t times d. Hence total attention cost per step would be 2 times t times d. Then total per step cost would be this. And for whole generation to t tokens will be this. Now with the help of little bit of mathematics, we can get an equation to compute number of operations. Let's put the values here to see how many operations we need to generate these 5 tokens, which will be 400 operations, and since we have only one layer, it won't increase further. So the big O notation for this will be O of t cube d. If we scale up the number of tokens to 100 with the same model architecture, then the number of operations would start to increase exponentially. Now we know that key and value for up to previous token doesn't change, so intuitively we can store them or cache them into memory. So let's see how caching can reduce the number of operations and make model inference faster. Let's make a list to store key and value respectively. And taking the same example, feed the first token to model and get the query key and value projection. Then it will go through attention mechanism to predict the next token. Since we know the key and value for previous token t-1 does not change, we can store them in their respective list. Now we'll send the both token to model again, but this time since we already store the key and value output for previous token, we'll fetch the cached value from the list and only need to perform computation for the new token in the same way and store the value of key and value in their respective list. And we'll repeat the process till we have all the tokens generated. But the question is, how much operations are we saving? Let's see. The operation cost for query, key and value projection will be 3D square. This operation will be constant since projection value for previous token are getting from the list. Now the cost for attention will be 2 times t, which is t times for dot product of query and key, and then the result times v. Combining them will give us this for single step T. To generate all the tokens, we'll perform sum over all generating steps, and by solving this, we will get our final equation to compute the number of operations. The time complexity with cache will be big O of T square D. Now let's see how much difference we made on the same example. Substituting value of tokens and model is giving us 120 operation, which is far more less than non-cache 400 operation. Scaling it to 100 tokens and comparing against non-cache version of model will appear like this, which is a huge difference. For comparison, 100th token without cache was taking 1.4 million operations, whereas with caching it's just 21.4 thousand operations. This is insane, but this insanity comes with a memory cost. We are storing values for key and value in memory, which is growing linearly. And remember that we are only having one attention head and one layer. Real models like GPTs have hundreds of layers with hundreds of attention head. So, to compute memory usage, we have this equation, which is 2 times number of layers in the model times context length times hidden dimension times the precision of floating point number, which is 16-bit, which will occupy 2 bytes of memory. So substituting values in the equation will get us 800 bytes for 100 token length or sequence length, which is not much, right? After all, we have gigabytes of memory, right? But hold on, this is for our imaginary model we made. If we apply on real model like Llama 3 8 billion parameter model, which is having 32 layer with 4096 hidden dimension, the memory consumption for generating 100 token will be approx 50 megabytes. With this much operation without cache, and if you cache, then this will be this much operation. Just imagine how much memory it would take for models like GPT-5 or Gemini 3 with trillions of parameters and serving on 100,000 of sequence length. That's why you see cached input pricing is 3 to 4 times low compared to normal input pricing on OpenAI pricing. And companies are fighting to get more and more high bandwidth memory, which eventually caused the memory crisis for normal consumer in the world. Anyways, the caching mechanism is called key value cache, and now you know why. Modern LLM uses more optimal techniques like LM cache for better cache management, but that's the tale of another video. Thanks for watching.